is talking directly from India. So it's a pleasure to have José Abel Hoyos Neto, or for the people who are from Unicamp in Manaus. And he's going to be talking about dynamical Griffiths phase. So thank you very much, José, for being here.
Thank you very much for this introduction. I would like to start thanking the organizers for this invitation and the opportunity to talk about this work, which was done in collaboration with the group of José Xavier at Uberlândia. And well, let's see what I have for you today is that I'm looking for disorder effects in the time evolution of closed quantum systems. And I will try to tell you the following message that rare regions, which is something that I will define soon, are very important for the dynamics, the unitary dynamics of random systems. And this is a result that I think it's counterintuitive, and we'll see why. So, okay. I'll go fast because I don't have much time, but what we are interested in the dynamics of closed quantum many-body systems, and there are many interesting phenomena that are currently being studied, as for instance, thermalization, the lack of thermalization, and this has been experimentally accessible nowadays, especially in these quantum platforms simulators. And one concept that appeared recently is the concept of dynamical quantum phase transitions, which is the following. Some physical quantities can be non-analytical functions of time, which is analogous to the partition function being a non-analytic function of temperature. So the quantity I'm going to study is this Loschmidt echo or amplitude, which is actually just a return probability of the initial state. So I prepare the state in some initial given or initial state, evolve it according to some Hamiltonian unitarily, and then you ask what's the probability to return to the original state. This function, this return probability, it's also we can call as a dynamical analog of the partition function, because it has all the flavors of partition function if we identify IT as inverse of temperature. So this rings the bell of defining dynamical free energy. And this dynamical free energy, we can study it using what we know from equilibrium phase transitions. For instance, we use the theory of the Yang-Lee theory of zeros of the partition function. So looking at these Yang-Lee or simply Fisher zeros, we know that the partition function can be non-analytic at certain temperature or thermodynamic external parameter like field. And this is known the following way. We can get a function in the complex plane. And this function in complex plane, you can always factorize it as long as it's non-pathological. In a part that is analytic and it's zeros. So when you take the log, that's what we want for obtaining the free energy. The non-analyticities are on the log of z's, the zeros, and so the zeros of the partition functions tells when where the partition function is non-analytic. And in analogy to the equilibrium phase transitions, where we should have zeros touching the real-time temperature axis, now these zeros can touch the real-time axis, and they can accumulate in lines or areas. And we'll see that examples of that. So to study. To be precise, the system I'm going to study is the transverse field easy chain, or the quantum easy chain, where you have interactions and quantum fluctuations. So the external field, transverse field, parameterize the quantum fluctuations. This is the equilibrium phase diagram, at zero temperature phase diagram. We have a ferromagnetic phase, we have a paramagnetic phase. This system in 1D is very special because you can map in free fermions and get analytical solution, especially if you put the periodic boundary conditions. And once you map in free fermions, you can solve via Fourier transform and Bogoliubov transformation, and you get analytical expression for the dynamical partition function, which is this productory here, and the K are the Fourier vectors. I will not going to tell you details about these equations here. I'm going to show you what that means. It means the following. Of course, I have to explain the quench, the dynamical procedure I'm doing. I'm preparing the system in H naught, which is the ground state of the Hamiltonian H naught. So I have a field, initial value of this field. I prepare the system in the ground state of this Hamiltonian, and then I quench H naught to H, and let it evolve after quenching this under this new Hamiltonian. In this case, in the case here, I'm putting H naught infinite, so deep in the paramagnetic state, every spins are pointing the x direction, and then I quench H from infinite to a finite H. When this finite H is less than J, meaning that we cross the phase transition, arriving from here to there, the zeros of the partition function, what are these balls or these points here, they accumulate in lines that cut the real time. And if you do a quench that do not cross the phase transition, these zeros accumulate in lines which do not cross the real time. So when the quench does not cross the transition, the partition function has no zero touching the real time, and the free energy is an analytic function. Always move C infinite class and so on. However, if you cross the phase transition, that's how the free energy, the dynamical free energy looks like. So at certain time instance, we find cusps, and these cusps are non-analyticities related to the zero that is touching the real time here. The points are for finite systems. I don't remember exactly 50, I suppose 50 sites. And the dashed lines is for the thermodynamic limit. These curves here are for finite system size. If you zoom in, you're going to see that the cusp is not really real cusp. The cusp is only real cusp in the thermodynamic limit. So this is when you go from the black curve is when you go from deep in the paramagnetic to deep the ferromagnetic phase. That's your quench is crossing all the way the transition, the phase diagram. And this is 1/3 for these guys here. So 2 point something is exactly this cusp, and you got another cusp in 6.7 something, which is these other cusp, and so on. Okay, so in general, you can ask, a dynamical quantum phase transition occur only when the quench cross the quantum phase transition? For this model, the answer is yes. But lately, many other models have been found where that's not the case. So there is no one-to-one correspondence between dynamical phase transition and equilibrium phase transitions. So, okay, now I'm going to to introduce this order, which is the one that I'm looking at. And I put this order in the coupling constant. So let's say the coupling constant distributed between some typical value, and there is a width here. And the phase diagram of this model is very likely, looks like a lot with the other model, the clean model. If H is very strong, you are deep in the paramagnetic phase. If H is very weak, you are deep in the ferromagnetic phase. So this is the conventional ferromagnetic phase, this is conventional paramagnetic phase. But when H is more or less in the middle, you're still in the paramagnetic phase, but you have what we call rare regions, where locally the J is greater than the field, so locally the system wants to be ferromagnetic in that region. So this is called Griffiths paramagnetic phase. And the important difference between the conventional paramagnetic phase and the Griffiths paramagnetic phase is that the spectral gap in this region here is 0, although you're still in the paramagnetic phase. And by duality, there is a ferromagnetic phase, a Griffiths ferromagnetic phase on the other side of the quantum critical point. So the reason why there is no spectral gap here is well understood. I'm not going through that. I don't have time. But let's do dynamics. So dynamics are for a standard quench for a quenched disorder system. So my disorder system is 50% J's strong and 50% J's that are weak. So instead of using a Gaussian, I'm going to take a bimodal distribution. So if I quench from the paramagnetic phase to something in the middle, the quench is from the conventional paramagnetic to the Griffiths paramagnetic. I'm not crossing the quantum critical point. I'm just having some couplings that are strong, these black, the dashed ones, and some that are weak, these black ones. And you do the quench and compute the free energy, the dynamical free energy. And I did that for different system size, 50, 100, and 150, and then you see what a mess you get. And if you have done that in the clean phase, in the clean case, no disorder, you should get something that is smooth and analytic. And instead, I'm getting something that is very weird, and the task is now to make sense of this mess. Because it's a lot of things that looks like non-elasticity here, but you increase the system, it appears, it disappears, it doesn't seem to have a consistent pattern. But I will try to show you that there is. So what I'm going to do is the following. I'm not going to take a random system like this. I'm going to take a system that has a single defect. So everywhere the system has coupling JB, B of bulk, except in this rare region, where the coupling is JRR. And I will vary JRR in this region of size L. And I will do the same thing. I'm doing the quench from this conventional paramagnetic to this Griffiths paramagnetic. And that's the following. Let's start with a rare region that is size 1, so there's nothing rare on that. And let's make this J rare region equal J bulk. It's 1/10 of H. Remember, I'm doing the quench from H infinite to some H. And the H is greater than all the G, so you are deep in the paramagnetic phase, and the accumulation line is here on the top, does not touch the real time. So I make this defect here, this rare region now equal to 2. And the zeros, they change. And I keep in 3, 4, 5, so that's my animation. Should be laughing about my animation. But what I want to tell you is that by the time when I reach the phase transition, of the local phase transition of this rare region, nothing's happened. The zero is still there. This migrating zero does not go below the real time. And when I go to 2 times and 3 times, nothing's happened. But okay, that's just a single defect. The single defect doesn't do much. So let's make it bigger, 2. And now two zeros migrate here. But not so much of things is going on. Now let's make 3. Oh, now 3 is interesting because 1 0 went down the real time axis. And make 4, 5, and the time that you make 15, you have a clear accumulation lines. So there is a migrating accumulation lines of zeros that migrate to here, and it's crossing the real time axis, and a real singularity is appearing in the free energy. And this is only because I have this rare region here. So the conclusion so far is that we have Fisher zeros that are induced by the rare region and is close to the real time axis. Well, that's the conclusion. The other conclusion is trivial, that we split these zeros in 2 sets. So there is one set that's up there and the one set that's down here. Okay, no, not a big deal. The thing is, how do we make sense of that? And the interpretation that I'm going to put forward is the following. The bulk and the rare region dynamics are decoupled in the following sense. Two open chains undergoing their own quench. So I'll cut the rare region from the bulk, and I will say, oh, the rare region is going through the quench, and it crosses its phase transition. But the rare region is clean, and when it crosses its phase transition, we know what happens. We get singularities. The bulk is clean as well, and the quench does not cross the bulk transition, so the bulk doesn't give any singularity. So I'm saying that these zeros here are due to the rare region, and these zeros here are due to the bulk. And so that's what I did. So I changed. What I'm seeing is that those zeros, now I put two accumulation lines. Before here, I just drew one accumulation line, but there are other accumulation lines to further times. And the second accumulation line is here. So changing the field, the quench field from infinite to some values, we see this migration of zeros. I showed you just a migration of 1, 0, but this is for a region of size 20, or I don't remember the correct size. But this is just to tell you that the zeros are doing something very, very non-trivial when they migrate. You could think that all zeros migrate to the first accumulation line here, but that's not true. From the second accumulation line of the clean, it migrates to the first accumulation line of the rare region. So it's something totally non-trivial and unexpected. Okay, so what I have here, I did the quench of the rare region. So I get this rare region, decouple it from the bulk, and do the quench. And this rare region gives me these zeros here, which are the crosses. And they are on top of these rare regions that we computed when you did for the entire system. And it's on top of that. It's amazing. It's a highly non-trivial result. And the same thing, the bulk is not on top. But I don't care, because the bulks are up there, up in the sky in the imaginary time, so they don't contribute to any non-singularity. So all the singularity will come from the rare region. So the second thing I'm going to tell is that if you put two defects, they do not talk to each other. So let me go, this slide is busy, let me go through that. So I have two rare regions, one of size 10 and another size 8. And I compute the zeros. The zeros are these black curves, these black dots. So there is black dots here and there is black dots there. There are two accumulation lines of these black dots, one for each rare region. And the black curve is below this red dashed one. I hope you can see it. If I erase one of these rare region, I put JRR2 equal J bulk, for instance, I have only a rare region. And if I compute the zeros are these orange ones here, which are on top of the one of sets of the black ones. And the corresponding free energy is this orange curve. Now I do the other way around. I erase this first rare region, put it clean in this side, and get only the second rare region. Those are the green ones, the green dots. The green dots are here on top of the black ones. And the free energy is this green one here. Now, if I sum the green and the orange, I get the red dash. The red dash is just the sum, the real sum. I just get this data and sum, and I get the red dash, which is on top of the black one, where I have the two rare regions. So the rare regions do not talk to each other. And why is that? The reason is the following. I'm doing dynamics, so I'm saying that the rare regions being far apart, they do not talk to each other because the bulk has a correlation length. And this correlation length of the bulk is still a well-defined quantity, because when I do the quench, I do not cross the bulk transition. So the bulk is practically in its ground state, where the correlation length is still a well-defined quantity. Okay, so this is more of the same. I do these quantities, these things, and I just check that always the same. But the last thing I want to tell you is the following. I compute the local energy, I mean, the local excitation above the ground state of the post-quench Hamiltonian. Phi ground state is the ground state of the post-quench Hamiltonian, and I'm computing the energy, the local energy of the evolved state. So what is EI? Here's this operator. I get the local transverse field, half of the coupling to the left and half of the coupling to the right. And I remove the ground state energy from that. And I get this. So I get a rare region of size 20, which is between sites 1 and 20. And I got another rare region of size 5, which is between sites 40 and 45. And the entire chain is 60. So you see that blue has no excitations. So the bulk is non-excited or has very few excitations, because you did not cross the bulk transition. But the rare regions, you cross the rare region local transition. So they are highly excited, because locally they are ferromagnetic and the initial state is a paramagnet. So they are full of excitations, and these colors means that. I also compute the, well, this is a continuity equation, so you can define an energy current. So that's the energy current, and the energy current is the panel B here. So there are energy currents going on inside the rare regions, but no energy current in the bulk. So you have the cone light that is expected, light cone, sorry, and nothing is going on to the bulk. So, okay, so that's what I have to tell you guys. If you have many, now that we know that the rare regions superpose, if I have many rare regions, which happens in the disorder, totally generic disorder case, each rare region will give you a singularity at the different times. If you are in the thermodynamic limit, they will accumulate densely here, and you have a region, a time window in real time, where this function is non-analytic. And that's what I'm calling dynamical quantum Griffiths phase. It's a region, it's a time window where this dynamical partition function is non-analytic function. And that's what I had to tell you. Thank you very much for your attention. I cannot hear the applause, but I suppose everybody's cheering to this great talk.
Yes, everybody. So Eduardo Miranda has a question.
Hello.
I don't know how, if I pass the time, but...
Hello, can you hear me, Jose? Eduardo here. He can't.
Sorry?
Can you hear me?
Yes.
Okay. Greetings from Brazil. This is Eduardo. How are you?
Good, you?
I'm good too. Excellent talk. I have the following doubt. You showed that the excitations are confined within the rare regions. Of course, the bulk has a gap because you're not at a critical point. So my expectation would be that if the energy of the rare region is large enough, it would leak into the clean region and would travel to the other side and then transfer energy from a rare region to the other. And apparently that's not happening here. You said there were light cones, but I can't really see the light cones there. But I would expect light cones for transfer of energy from one rare region to the other. So the question is the energy larger than the gap so that you can transfer energy from one to the other? If it is, why doesn't it transfer? And if it's not, then shouldn't you excite it to a higher energy so that it can leak out?
Yeah, this is a great question, which opens many discussions. What I have to tell is the following. Yes, energy will tunnel from one region to another, and this will happen at very, very long times. All these physics I'm telling you is short-time physics. So all these singularities that are happening here, you see, this is short-time physics, 1 HT or 2 HT or 5, 6. And we know that, well, I was going to the, so while to transfer energy, it has to bounce many times because it has to tunnel through the bulk. And the bulk is gapped, it does not accept any quantum of energy, and the quantum of energy inside here has a mismatch with the bulk. But eventually it will tunnel, but it will be very long energy, very long time scales. So all these fields I'm telling you is correct for short time scales. These will happen for short time scales. For long time scales, then there is energy transfer, and if you break integrability, the system may also thermalize itself. So this physics I'm saying short time physics is very different from the equilibrium Griffiths time, Griffiths phase, Griffiths physics, which is long time, as you are very aware of that, and the rare regions are not excited at all, or very weakly excited. Here is the opposite way around. I hope that yeah. And even if the gap was not, the bulk was not gapped, the bulk is in a different phase of the rare region. So when you excite the rare region, the energy, these light cones is carrying local quantum numbers. Like we know that in the ferromagnetic case, you have instantons here, but you don't have instantons in the bulk. But if the bulk was gapless, it is in a different phase. Even though the bulk is gapless, I claim that the excitations will not decay right away to the bulk because of emergent quantum numbers. So it will decay eventually, but it takes some time.
Further questions?
Thank you very much for the nice talk. I was going to ask about the... Can you listen to me, José?
Yes, very, very faint, but go on.
I'll try to speak louder. My question is about the autocorrelation function and the distribution of the rare regions. Can you comment about what's the difference between the dynamical quantum Griffiths phase with and without disorder?
What I'm saying, I'm not sure if I heard completely, but the question is that I didn't use disorder. That's what you meant, because I use only cut and tail rare regions. Is that correct?
Yes.
Yeah. The thing is, I'm trying to say is that this singularity in the dynamical free energy is due to these rare regions, because they are rare. Why they are rare? Because they are large. They need to be large, so you have an accumulation line of zeros that are sufficiently close to the real time. So I only need that these rare regions exist. If they exist, this accumulation line exists, and the non-elasticity exists. So I'm just trying to tell you is that, well, in the real world, you have many things, but you also have the rare region, because the probability of finding this rare region is finite. You can flip the coin many times and get many heads. It's exponentially rare, but that's not a problem at all. I only need that the Fisher zero be there. The Fisher zero being there, the dynamical free energy will be non-analytic. So that's I suppose, I hope that answers your question. I'm not sure if I was totally satisfied. But,
yes, thank you very much.
Any further questions? So if not, let's thank Jose again. Thank you very much.
So it's great to be here, guys, and I hope that you are having a great time in this which seems very exciting workshop. I'm sorry I'm not there.
Yeah. Hopefully next time.